All right, we are going to talk about a strong acid, weak base titration. And I have a titration curve that shows the strong acid, weak base titration here. Notice that we start off at a high pH and then go down from there. So when you're doing this strong acid, weak base titration, the initial pH should be basic. And when you're calculating the pH initially, it's very similar to a weak acid strong base titration, except for now we're going to be dealing with Kb. So Kb is going to be equal to x squared over the initial concentration of your base. So again, remember x in this case, instead of being equal to hydronium ion, is going to be hydroxide. So I can solve for my hydroxide, which is x, and it's going to be the square root of Kb times the initial concentration of your base. And then as soon as you have that, you can calculate your pOH, and then you can calculate your pH. So it's very, very similar to the way we calculate the initial concentration of a weak acid. Now, if you look at the area before the equivalence point, so in this area right here, it's really going to depend on where you are on the titration curve. If you're more up here, then you should have a basic pH, but as soon as you start getting down in this area, don't be surprised if you have an acidic pH, even if you are before the equivalence point. So, before the equivalence point, you should have a basic pH, but it may be acidic, especially if the millimoles of your acid and base are really close together. So when you are before the equivalence point, it is the buffer region. You need to be very careful using the Henderson-Hasselbalch equation in the buffer region of a weak base strong acid titration. And that is because the Henderson-Hasselbalch equation is in terms of pKa, and we're dealing with Kb. So not only do you have to convert your pKb into pKa, you also have to flip the conjugate acid and base. So just make sure that you're paying close attention to that. I always do it in terms of the Kb expression. So before the equivalence point, you can solve for the concentration of hydroxide. Remember, you're going to have both base and conjugate acid in solution. So you can do Kb times the concentration of your base divided by the concentration of your conjugate acid. And as soon as you have that, you can solve for the pOH and then convert it to pH. Now at the equivalence point, your pH should be acidic. And that is because now the strong base is going to take over. So what's going to happen is you're only going to have your conjugate base you're only going to have your conjugate acid in solution. So then you're going to have to look at the Ka of your conjugate acid. So when we calculate for the concentration of hydronium ion, it's going to be very similar to that of a weak acid. Now keep in mind that you're going to have to solve for Ka, which is just Kw over Kb. And then we have our Ka expression, which is just hydronium ion times your base over your initial conjugate base. Or sorry, conjugate acid. We'll rewrite that. I didn't mean to erase all of it, but that is what happened. There we go. So remember, your pH should be acidic. Now, finally, when we are beyond the equivalence point or past the equivalence point, we should have an acidic pH, but it should be more acidic. Because at this point, we only have our strong acid in solution. All of our base has been consumed. So it should be a pretty acidic pH. So what you want to do is subtract the millimoles of your acid minus millimoles of your base. And then that will give you your excess millimoles of your acid. Then you can divide that by your total volume. And remember, since this is a strong acid, that will give you the concentration of hydronium ion. As soon as you have your concentration of hydronium ion, you can solve for pH. All right, so let's look at an example. So let's look at a 25 milliliter solution of 0.1 molar ammonia is titrated with a 0.125 molar nitric acid solution. Calculate the pH at 0, 10, 20, and 30 milliliters of nitric acid. All right, so the pKb of ammonia is 4.76. So let's look at A. A is 0.0 milliliters of acid added. So what that means is we only have base in the solution. So I can calculate my Kb. We can do that by taking Kw. That's not what I wanted to do. We can take the antilog of our pKb. So I get 1.74 times 10 to the negative 5. Now, as you all know, I always carry out every single one of my sig figs. So if you do these calculations and you get something slightly different, but it's only because you're using the 1.74, that's probably why. So I know that the concentration of hydroxide is going to be equal to the square root of my Kb times the initial concentration of my ammonia, which is 0.10. And when I do that, I get 0.00132 molar. So I can plug that into my pOH equation, and that gives me 2.88. And when I calculate the pH from that, I get 11.12. So my initial pH is 11.12, which makes sense because it should be basic. All right, let's look at part B. This is at 10 milliliters. So the first thing I'm going to do is calculate the millimoles of both my acid and base. So I have 10 milliliters of my acid. I'm going to multiply that by the concentration of my acid. And that gives me 1.25 millimoles of my nitric acid. Now I can calculate my millimoles of base. And I get 2.50 millimoles of my ammonia. So when I set up my neutralization reaction, I'm going to have ammonia reacting with nitric acid to yield water and ammonium nitrate, or nitrate rather. Now, I want you to keep in mind that we don't really care about this nitrate. It is a spectator ion. It's just there to balance charges. You could easily write this as NH3 plus H plus yields NH4 plus. Either way works. So now I am going to write in my millimoles. And my acid is going to be fully consumed. That is my limiting reactant. So you'll notice that we have equal parts acid and base. So if you look at our equation that we wrote previously, I know that the concentration of hydroxide is equal to Kb times the concentration of my base divided by the concentration of my conjugate acid. And remember, that simply comes from the dissociation of your base. I'll write it small up here. So that yields NH4 plus OH minus. Our equilibrium expression for that will be ammonium times hydroxide divided by ammonia. And when we solve for that, when we solve for hydroxide, then this is the equation that we'll get. Now notice we have equal parts ammonia and hydroxide, so that means the concentration of our hydroxide is going to be equal to Kb. So I can solve for my POH, and then I can use that to solve for my OH, pH, and I get 9.24. All right, notice I did not use the Henderson-Hasselbalch equation. If you wanted to use the Henderson-Hasselbalch equation, you could, but you would just have to change your Kb into Ka and then convert it to pKa. And in this case, since you have equal parts conjugate acid and base, you are going to have your pKa equal to your pH. So now let's look at 20 milliliters. So I already know that I have 2.5 millimoles of my base, and I can calculate the millimoles of my acid, which will also give me 2.5 millimoles. So what this means is they are equal, so we are at the equivalence point. And remember, at the equivalence point, the millimoles of your base is going to be equal to the millimoles of your acid. And for a weak base, strong acid titration, then that's also going to be the millimoles of your conjugate acid. So what that means is I know that I am going to have 2.50 millimoles of my ammonium. And keep in mind, all that comes from is the neutralization reaction. And I have equal parts here. So these will both be consumed and added to the other side. So now I have none of my base and my acid left over, and I only have conjugate acid in solution. So the first thing I need to do is calculate the concentration of my ammonia. So I'm going to take my millimoles and divide it by the total volume, where we have 25 milliliters of my base plus the 20 milliliters of acid that was just added. And when I do that calculation, I get 0.0556 molar. So now, remember, we have two equations going on here. So I have my neutralization reaction, but then I also have the dissociation of ammonia in water. So I can also calculate Ka, which is just Kw divided by Kb. Which is 1.74 times 10 to the negative 5. And when I do that, I get 5.75 times 10 to the negative 10. So this is similar to a weak acid situation. So the concentration of my hydronium ion is going to be equal to the square root of the Ka times the concentration of my conjugate acid. So when I plug my values in for this, we'll get 5.75 times 10 to the negative 10 multiplied by the concentration that I just calculated. We take the square root of that, and we get 5.65 times 10 to the negative 6. And when I negative log that, I get a pH of 5.24. Now, this is at the equivalence point with a weak base strong acid, so keep in mind the pH should be acidic. So this pH does make sense. Finally, let's look at part D, which is 30 milliliters of my acid. I still have 2.5 millimoles of base, and I can calculate how much acid I've added. And I get 3.75 millimoles of my acid. So here I can see I'm beyond the equivalence point because I have more acid in solution than base. So if you recall, all I have to do is calculate the concentration of my acid. So I'm going to take my 3.75 minus 2.50, which will give me 1.25 moles of excess nitric acid. Now I can calculate the concentration of my nitric acid, which is going to be equal to the concentration of my hydronium ion, because this is a strong acid situation. So we have 1.25 millimoles of nitric acid, or I'm just going to use hydronium ion now, divided by my total volume. And that gives me a concentration of 0.0227. Now, when I get the pH of this, all I have to do is negative log that value, and I get a pH of 1.64.